Our next theorem deals with the continuity and differentiability of inverse functions. The theorem goes like this. Let f be a function whose domain is an interval I. If f has an inverse, then the following statements are true. The first statement says that if f is continuous on its domain, then f inverse is also continuous on its domain. And the second part says that if f is differentiable on an interval containing c, and f prime of c is not equal to 0, then f inverse is differentiable at f of c. Now, before we begin the proof, we have to define some terms. We say that f is strictly increasing on an interval if whenever x1 is less than x2, then f of x1 is also less than f of x2. We say that f is strictly decreasing on an interval if whenever x1 is less than x2, then f of x1 is greater than f of x2. And finally, we say f is strictly monotonic on an interval if it's either strictly increasing or strictly decreasing. So now we have to show that if f is continuous on the interval I and has an inverse, then f is strictly monotonic on that interval I. Here's how the proof of that statement goes. Suppose that f were not strictly monotonic. Then there would exist 3 points, x1, x2, and x3, in the interval I, such that x1 is less than x2 is less than x3, but f of x2 is not between f of x1 and f of x3. And in fact, without loss of generality, why don't we assume that f of x1 is less than f of x3 is less than f of x2, as indicated in the diagram here. Here's x1, x2, x3, f of x1, f of x2, f of x3. Well, by the intermediate value theorem, there exists an x0 between x1 and x2, such that f of x0 equals f of x3, so f is not one-to-one and cannot have an inverse, so f must be strictly monotonic. Because f is continuous, the intermediate value theorem implies that the set f of x, such that x is in I, forms an interval j. Let's assume that A is an interior point of j. From the previous argument, f inverse of A is an interior point of I. So, let epsilon be greater than 0. There exists an epsilon 1 less than epsilon and, of course, greater than 0, such that the interval I sub 1, which has left endpoint f inverse A minus epsilon 1 and right endpoint f inverse A plus epsilon 1, and that interval I sub 1 is contained in the interval I. Because f is strictly monotonic on I sub 1, the set of f of x's, such that x is in I sub 1, forms another interval, j sub 1, inside j. We've illustrated this in the diagram here. So let delta be greater than 0, such that a minus delta, a plus delta is contained in the interval j sub 1. Finally, if the absolute value of y minus a is less than delta, then f inverse of y minus f inverse of a in absolute value is less than epsilon 1, which is, of course, less than epsilon. So we've shown that f inverse is continuous at the point A. And a similar proof can be given if A is an endpoint. And that finishes the proof of part 1. Let's now prove the second part of the theorem. And let's begin by considering the limit definition of the derivative of f inverse at the point A. And that definition says that the derivative is equal to the limit as y approaches A of the quotient f inverse of y minus f inverse of A divided by y minus A. And of course, A is in the domain of f inverse, and here we're assuming that f inverse of A equals c. Because f is differentiable on an interval containing c, it's continuous on that interval, and hence so is f inverse at A by the first part of the theorem. So y approaching A implies that x is approaching c. And you have the following. The derivative of f inverse at the point A equals that limit definition as y approaches A f inverse of y minus f inverse of a over y minus a. But that's the same as the quotient x minus c over f of x minus f of c, where now we replace y approaching a with x approaching c. Then we flip the fraction down, and we have the limit as x approaches c of 1 over the quotient f of x minus f of c over x minus c. Well, the limit can move into the denominator, and we have that that's equal to 1 over the limit of that quotient, f of x minus f of c divided by x minus c. But that's nothing more than 1 over f prime of c, the derivative at c. So, the derivative of f inverse at a exists, and hence f inverse is differentiable at f of c.